Today we're going to look at some applications of the exponential and logarithmic equations that we were working with yesterday. These applications you've probably seen before, but they all center around this idea of what is called exponential growth It doesn't look like a G. Growth, there we go. Exponential growth or exponential decay. And the idea behind exponential growth or decay is that there is some starting value that is multiplied by something repeatedly to an exponent. You might say that equals y. And one great example of this that we've talked about before is compound interest. In compound interest, the final accumulated future value is equal to the principal present value multiplied by something several times. That's the interest multiplier of 1 plus r over n to the nt power. So we could now start to look at questions such as how long will it take a $10,000 investment to grow to $25,000. If it is invested at 8% compounded weekly. Plugging the information we have into the compound interest formula, we got the accumulated final amount of $25,000 is equal to the principal starting amount, present value of $10,000, times 1 plus r, which is 0.08, over n, which is 52, to the nt, 52 times time. And then we can go about solving this equation for the variable t, or time. Notice that t is in the exponent, so we're going to get the part with the exponent alone, and we do that by first dividing out the $10,000. That's going to give us 2.5 is equal to 1 plus 0.08 divided by 52 to the 52t. Now we notice that the variable is in the exponent, and the way we get it out of the exponent is we're going to take a natural log of both sides of the equation. That's going to give us, there's those disappearing numbers again, that's kind of odd. That's going to give us the natural log of 2.5 is equal to the natural log of 1 plus 0.08 divided by 52 to the 52t. And we know that an exponent comes out in front of the log. So now we have the natural log of 2.5 equals 52t times the natural log of 1 plus 0.08 divided by 52. Well, we're solving for the t, so we'll divide by everything else, by 52 natural log of 1 plus 0.08 divided by 52 on both sides. So the 52s are gone, the natural logs are gone. What's left is that t equals the natural log of 2.5 divided by 52 natural log of 1 plus 0.08 divided by 52. And we can do this on our calculator. Remember on the calculator, when you hit natural log, though, it's going to automatically open a parenthesis, so make sure it gets closed. Also remember on the calculator, we're going to need to put a set of parentheses around the entire denominator so that we know the denominator all stays on the bottom. So let's put it in the calculator. We push the natural log of 2.5. Remember to close the parentheses on the natural log. Divided by, parentheses for the denominator, 52 natural log of 1 plus 0.08 divided by 52. Close the natural log, close the denominator, hit enter, and we get 11.46. Time is equal to 11.46 years. So in 11.46 years, not quite 11 and a half years, that investment of $10,000 will grow to $25,000. Let's do another compound interest problem. Let's say we've got a $3,000 copier that will need to be replaced in 7 years. How much should be invested now at 12% compounded semi-annually? Using the same formula for our compound interest, the accumulated final future amount that we want is $3,000 is equal to, we don't know the present value of that money, that's what we're looking for, times 1 plus the interest rate of 0.12 divided by n, semi-annually is twice a year, to the 2 times 7. This one's nice because we can get the p alone. The easiest way to do that is to just divide by the 1 plus 0.12 over 2 to the 2 times 7 power. So let's do that. Divide by 1 plus 0.12 over 2 to the 2 times 7 power. Pull up our calculator and we have 3,000 divided by parentheses 1 plus 0.12 over 2 raised to the, now you may need parentheses if you're on a TI-83, 2 times 7 power, 132690. 1326.90 is equal to that principal. Starting present value. Let's try another problem. Very similar, though. Let's hop over to continuous interest. And you may recall with continuous interest, A, the final accumulated future value is equal to the present value times e to the RT. And so I could ask how long it would take for $800 to grow to $1,000 at 9% continuous interest. Well, the final accumulated value, future value of 1,000, is equal to $800, our present value, times e to the r, which is 0.09, times t, that's the time we are looking for. Again, to solve for the part with the exponent, we need to first get rid of the part that doesn't have an exponent. So we're going to divide by 800 on both sides. And that's going to give us 5/4 or 1.25 equal to e to the 0.09t. And then again, to get that t out of the exponent, we take the natural log of both sides. That gives us the natural log of 1.25 is equal to the natural log of e to the 0.09t. And what's nice about this is the 0.09t is going to come out front, and the natural log of e, remember the base on natural log is e, and so those undo each other. So what we're going to do is just have that exponent 0.09t, the natural log of e is gone, is equal to the natural log of 1.25. Quickly get t alone by dividing by 0.09 on both sides. And t, the amount of time it's going to take for this $800 to grow, is the natural log of 1.25 divided by 0.09, 2.48 years. The $800 will grow to $1,000. Just like we can solve for an interest rate, just like we can solve for an amount of time, we can solve an equation for an interest rate instead. Let's ask what interest rate will grow to, let's do 7,250 if $5,000 is invested for 4 years. Continuous interest. Well, we know the final value we want is 7,250 is equal to the principal value of 5,000 times e to the r, which we don't know, times 4. I'm going to write 4r. And then from here it's going to solve pretty much like it solved before. Get the part with the exponent alone by dividing out the 5,000. So we have e to the 4r equals, let's see if that comes out nice, 7,250 divided by 5,000, 1.45. If it didn't come out nice, I would just keep the fraction. But since it did come out to a nice 1.45, we can roll with that. Now, to get the exponent out of there, we take a natural log of both sides. So we have the natural log of 1.45 equals the natural log of e to the 4r. And of course, anytime you've got something inside the exponent, inside a logarithm, it comes out front. And the natural log of e is 1. So we're just left with the natural log of 1.45 equal to 4r. And we get r alone by dividing both sides by 4. So that would be the natural log of 1.45, close the parentheses, divided by 4, 0.00928. Sorry, I got an extra O in there. 0.0928. So That's about a 9.28% interest rate. Get the percent, we move the decimal twice. So at 9.28% interest rate, the $5,000 will grow to $7,250 in 4 years. Now, a question we're often interested in with finances is not just the compound interest rate, but instead, what is the effective interest rate, also known as the annual yield. Basically, if the interest was paid just once per year, what would the interest rate be? Well, we'll call it R sub E, the effective interest rate. We can find by using that 1 plus R over N to the NT thing. Except we're talking about 1 year, so T is 1. So 1 plus R over N to the N. And then subtract off that 1. Similarly, with continuous compound interest, we can take e to the RT, with t being 1, and subtract 1 off of that. And that's going to give us the effective interest rate that you're earning in a year on some account. So, for example, if you were offered 7% compounded monthly, and we wanted to find the annual yield, since it's compounded monthly, that's the bigger formula. 1 plus 0.07 divided by 12 is the monthly, to the 12th power minus 1. So in parentheses, 1 plus 0.07 divided by 12 raised to the 12th power. Be careful here. Make sure you are out of the exponent before you subtract 1. 83s will do it automatically. 84s you need to actually get out of the exponent. And we find that's 0.7229. So move that decimal point twice. 0.07229, I should say. So now if you move that decimal point twice, you get 7.229% is the annual yield, the effective interest rate. Because that 7% compounded monthly is split up over the entire year, and compound interest earns interest on the interest, in effect, what you have made annually for your interest rate is 7.229%. That 229 is that interest on interest throughout the year. How about this question? What if we did 8% compounded continuously? Well, 8% compounded continuously, that's the e to the r, 0.08, minus 1. E we get off of second, ln, gives us the e, to the 0.08, get out of the exponent, minus 1, and we find 0.08329. 0.08329. Move that decimal point twice, and we have an annual yield of 8.329%. Because it's compounded continuously, that interest on interest has earned an extra 0.329% return over the course of a year. But we don't have to just find the annual yield. We could know the yield and figure out what the interest rate is. What continuous interest rate will have in annual yield of 12%. In other words, e to the r minus 1 is going to equal 12%, or 0.12. Well, first we need to solve for the part with the exponent. We get that alone by adding 1 to both sides. So e to the r equals 1.12. Take the natural log of both sides. The natural log of e to the r is equal to the natural log of 1.12. And this is nice because the r comes out front and the natural log of e is 1. So we have r is equal to the natural log of 1.12. On the calculator, the natural log of 1.12 is 11.33%, 0.1133. Or if you move the decimal point twice, 11.33%. Interest rate, compounded continuously, will become an annual yield of 12%. So nothing really new in this video, just taking some of those ideas of logs and exponents and how we use them to solve equations to find various variables in the compound interest formulas. A short video today because we're focusing on the application. Take a look at the problems, bring them to class, come with questions, and we will see you then.